Thank you, Dr. Plazas. That was a great daily space, guys. I mean, you guys all had great questions for him at the very end there. I really enjoyed the discussion myself, kind of like lurking in the background there. All right. Well, before I get started, I want to quickly state that my co-host and fellow coworker Joe Myers will not be able to join us today, unfortunately. Um, so I'm going to try to, keep the party going without him. So here we go. So today's topic will be about our very own star, the sun. Um, and of course, since Joe is unable to be with us today, I'm going to try my best to keep up with the chat. And feel free to ask questions, give comments. And so, wait, can you guys see me? I just saw a comment by Guido stating, "Stay tuned for Matt Richardson and Joe Myers." All right, perfect. All right. So, the sun. I typically would start off by asking Joe like what are interesting things you know about the sun, but since he's not here, I'm gonna go ahead and say what I think is interesting about the sun. The fact that without it, of course, there wouldn't be life here on Earth, is probably one of the most important things I think that's very interesting about the sun. And so we're gonna go ahead and just get talking about initially, how was the sun formed? Exactly. Big, bright, warm, full of energy, and does a lot of other great stuff for us. What's up, guys? Hey, Adam. All right, so with that said, let's go ahead and talk about how the sun was formed. So, billions of years ago, and I believe I've kind of went into this story before. Hopefully, I'll provide a little bit more detail here. But billions of years ago, we initially started off with a big cloud of gas and dust, molecular gas and dust, from which it's a great place for stars to be born. That's why these objects known as nebula are great places or great stellar nurseries for the creation of stars. And so initially we start off with this nebula, and within the nebula, we start to over time acquire clumps of gas and dust. And these individual clumps of gas and dust are essentially the beginnings of stars and whatever objects will be orbiting them. And so, again, over time, due to the self-gravity within these individual clumps, they begin to coalesce or begin to come together from gravitational interactions between the gas and dust within the clouds, within the clumps. A critical point is reached when the clumps of gas and dust begin to essentially form what would look like a star in the very center of the clump, and on the outskirts you kind of get these disks. And the reason why you're getting the disks is because of the fact that as these clumps of gas and dust contract onto one another, or contract into itself, it begins to spin up more and more. So the outskirts of the clump will begin to flatten, while the interior of the clump can maintain its spherical shape and would form your host star or stars, depending on the conditions of the clump. So we're kind of now in the issue of where we're at the very bottom of our image here, where in the center we have our star that's been formed. It's a very young star, hot. In the case of our own star, the sun, it's now gone on to a particular portion of a graph known as the HR diagram, where it's now sitting on the main sequence. And so, unfortunately, I don't have an actual graph of the main sequence, but basically what's happening now with the star is that it's begun to fuse hydrogen into helium within its core. And we'll get more into the different layers of the sun in a second. But the sun is now it's a star, a main sequence star, and it is now fusing hydrogen into helium within its core. Surrounding it is basically a disk of steel, gas, and dust that can be used to later, of course, form the planets and other solar system bodies that we discussed in the previous streams. But today's stream will focus primarily on the sun. So we now have our sun, and so the next thing we would want to talk about, of course, is, well, what does the interior of the sun look like? And again, guys, I'm going to try my best to keep up with the comments here. I think what I might want to do really quickly before continuing is pop out the chat, but this will require me to actually log in, which I have not done yet. So just give me a quick second to do that, and we'll continue with the discussion. But speaking of the sun, I hope everyone's day is going well so far. Here in Clarksville, Tennessee, the weather's quite nice outside. It's been nice, at least for the past week. All right, here we go. I now have the option to pop out the chat. Oh, there goes a little bit of, let's see. Let's mute that. All right, perfect. I can get rid of this. Okay, so talking about the solar interior. Here I have a diagram showing what the inside of our sun looks like. Of course, we're going to start from the inside going out. And starting from the inside going out, we see at the very center or at the very bottom of this image showing the solar interior is our core. Now, the core, as stated here, is at a temperature of roughly 15.7 million degrees Kelvin. And this is a perfect temperature for the core because it allows for the fusion process, that is converting the hydrogen content within the core of the sun to helium through nuclear reactions. And so as you move out from the core, from this very dense and hot region of the star, you begin to go to regions of the sun that are less dense, one, and less hot, two. And so moving on from the core, we go on to what's known as the radiative zone. And so to kind of explain what's going on here, there's three modes of or three forms in which energy moves from one place to another. These three forms would be known as either the radiative energy transport, or energy transport through convection, or energy transport through conduction. So in the case of a star like our sun, the preferred method of energy transport, energy that is being created by the core of the sun, is through the process of radiation. And so over a good length of the radius of the sun, we have the radiative zone, which basically corresponds to basically meaning that the sun's preferred method of energy transport through this particular zone is through radiation. So a lot of light's being generated and it's being able to propagate through this zone of the sun, and eventually we come to the next zone, which is the convection zone. Now there is another portion of this diagram that I have no idea what it means, honestly. The tachocline or tachocline. I have no idea what that is, guys. I apologize for that, but these other zones I'm pretty familiar with. And so we move on from the radiation zone to the convection zone. And in this zone, the primary means of energy transport is through the process of convection. And basically what's happening is here is that you have bulk material of the sun moving from one point in the sun to a higher point in the sun, and depositing whatever energy that they're carrying with them to a higher portion of the sun. And so that's essentially what's occurring within this particular zone of the sun. Eventually, we end up going to the outermost layers of the sun, starting off with the photosphere, which is kind of like known as the surface of the sun. And then we move up into the atmosphere of the sun, which is composed of, well, it says here the corona, but I'm remembering that there's actually three portions of it. There's the corona at the very top, then underneath the corona there's the transition zone, and then underneath that there's the chromosphere. But the key things I want to note about this diagram is that along the right edge of the diagram, you kind of see how the temperature changes as a function of the radial profile of the sun, and along the left edge, which is also quite just as interesting, you see how the density changes with changes as a function of radius of the sun as well. Now, there's two more features here that are also just as interesting as the rest of the diagram, and that is on the left-hand side of this diagram, you kind of see the paths taken by individual photons and individual neutrinos. Take a quick moment to look at Thank you, Finring. That is perfect example. Okay, that's from Wiki. Okay, I was gonna say like that's a perfect definition for that. But thank you for finding that for me. But yeah, honestly, when I was learning about solar interiors and how to build a star, we one of my courses we end up building a star, computationally speaking, building a star. I knew nothing, heard nothing about that particular boundary between the convection zone and the radiative zone. But nevertheless, it's very interesting though. And so the things I wanted to point out here are the paths that are taken by the photon and the neutrino. So of course, within the interior of the star, we essentially have fusion occurring and we're producing energy. And there's basically two forms of energy that are getting out from the interior. One form of that energy are photons, right? And those are the essentially the things we are actually able to see via all the various instruments we have, or just by our naked eyes. We're able to see a tiny bit of the light that's being generated by the core of the sun. But the other thing is actually very interesting that's being generated within the interior of the sun are these neutrinos. And so the importance of the neutrinos, though, the fact that they're coming from the sun, and we have an idea that they're coming from. Well, we had an idea. We now know they're coming from the interior of the sun. Is that neutrinos are related, are heavily related to um, nuclear nuclear interactions, which is one of the reasons why initially we believe that the center of the sun was being fueled by um, thermonuclear interactions. And so as you look at these particular drawings, or not drawings, but basically depictions of the paths that could be taken by either a photon or a neutrino, you kind of see with the photon, it kind of takes this crazy it's a really crazy path, right? And so what's happening is essentially as the photon is escaping from the core and moving out towards the outer layers of the sun, what ends up happening is it gets absorbed and re-emitted in random directions. And so it can take a very, very long time. I think I remember something like on the orders of hundreds of thousands of years, maybe millions of years, for a photon to just essentially escape the sun and be able to propagate through the interstellar medium, or basically our solar system. However, neutrinos, on the other hand, as you can see, can for the most part take a pretty much straight path. And the reason being is because of the fact that neutrinos are really low mass, fast moving particles, and their interactions with other particles are very low. So for the most part, they're able to just pretty much just zip right on through the solar interior and propagate to the rest of the universe wherever they may go. And so those were the two key things I actually liked about this particular image. And we'll probably revisit the idea of neutrinos later if anyone has any questions about them, or photons that are being generated by the interior of the sun. But I guess there's also one more thing I want to mention actually, and the fact that these photons that are being generated by the sun, they take on a very specific shape actually. Blackbody radiation. If you guys get the chance, you can go to Wikipedia and you can type in blackbody radiation and look it up. But the interior of the sun produces these photons, and the shape that they end up yielding is what's known as a blackbody curve. Um, and from that blackbody curve, you can actually estimate what the surface temperature of the sun is, which in this case is showing a value of 5,700 Kelvin. Okay, so with that said, we can now move on past the solar well, we're going to actually stay within the solar interior because another key question, of course, is, well, how do we know this information? Well, what we're seeing here is actually an image related to the sun that corresponds to studying the oscillations of the sun. And this particular type of science is known as helioseismology. But before we actually even knew that we could take the light from the sun and extract this helioseismic information from it, we for the most part already had an idea that at the very least within the core of the sun um, there had to have been nuclear interactions occurring for the simple fact that we are seeing neutrinos, which, like as I stated before, are known to be related to nuclear interactions. And so, but basically, we were able to better get an idea of what the solar interior looked like. And of course, before this, there were models, and those models had to, of course, take into consideration, well, how were we producing the neutrinos, as well as the radiation, and how was it getting out? But the picture became clearer with the advent of helioseismology. And so, basically, what helioseismology is the study of waves that are being produced within the solar interior. And so what I'm kind of showing with this image is a particular mode of oscillation that occurs on the surface of the sun. So I'm going to talk about a particular oscillation mode known as the P modes, which is short for pressure modes. In fact, pressure modes is the way in which you and I are able to hear each other. Basically, what P modes are, or pressure modes are acoustic waves. Um, and so what's happening with these P modes and how they're being generated is due to the process of convection. And so on the surface of the sun, what we're having is these up and down motions of or these convection cells, which cause up and down motions on the surface of the sun. And one particular type of mode that you may be able to see with these up and down motions is what we're seeing here. So to kind of better explain what we're looking at here is, if you were looking at the surface of the sun, on the surface you'd see high points which could correspond to the red squares essentially that are being shown in this image, and you'd have low points which could correspond to the kind of light bluish regions on the surface of this image. Now you can get this information by studying the light coming from the sun. More specifically, looking at a particular region of the sun and studying these up and down motions by calculating radial velocities. Um, and then there's a lot more to the process, of course, but you can essentially extract out this helioseismic information and be able to get a clearer understanding of these modes of oscillation, or these acoustic modes, and to kind of give a better picture of what's going on here, with at least what's going on within the interior of the sun. What we're having is, and I want to quickly take a moment to look at comments. But you do hate real modes that make the bass in my music non-linear. Oh man. Um, it's funny because, but yeah, well basically P modes are basically yeah, they're basically just exactly how we're able to hear one another. So acoustic modes are, if I'm remembering correctly, they're longitudinal waves. And the way in which it works is there's something within our body that essentially vibrates the molecules. And basically, what's happening is you kind of have this whole collision effect where one molecule hits another molecule, bounces back, but transfers energy to that other molecule. It moves forward, hits another molecule, and eventually that information, that in the energy is propagated from wherever the source is to wherever the instrument that's picking up that information. But that's essentially what the P modes are. But what's happening within the solar interior is that you have these different modes of oscillation. And one way to be able to characterize these different modes um, of oscillation is through spherical harmonics. I'm not going to go too much into spherical harmonics right now, but you can actually use spherical harmonics to describe the pattern that I'm showing here for the surface of the sun. And there's many of them. There's many different modes of oscillation. But if you were to characterize them specifically by one of the spherical harmonic integers, the L value, there's actually three of them if I'm remembering correctly. There's the N value, the L value, and the M value. But in particular, we're looking at the L value, and what you kind of see here is the fact that for different values of L, you get different. You get different structures for the oscillation modes. But two, which is more important, depending on the L value that you're actually studying, you can be probing different portions of the interior of the sun. As you can kind of see here, if you have a high mode, a high L value mode of oscillation, you're kind of only probing, you're shallowly probing the interior of the sun. However, as you begin to move closer and as you begin to try to get deeper and deeper into the sun and kind of get an understanding of what the internal structure looks like, you're going to of course be looking at L values that are much lower. And the reason why we're even able to do all of this is because sound, as it propagates through air, or the way in which it's able to propagate, not even necessarily through air, but through any medium, it's going to be dependent, of course, upon the temperature and density of the medium, which is the reason why, if I go back 2 slides, we can kind of see as you move through the interior of the sun and you look along the sides of this diagram, the temperature is changing as well as the density. And these modes allow us to kind of get a sense of how these changes are occurring by studying these modes. So I want to quickly, of course, I want to make sure I'm keeping up with comments here. So the way in which we're able to know it is by looking at the light, and then what you do is you or at least with one particular project that I know of known as Gong, the Gong which is short for Global Oscillations Network Group. You can look them up online, but basically they have helioseismic data, and the way in which it's done, or the more simplified way of explaining it, is you look at the light coming from the sun, and from this light you process it such that you look at the radial velocities, um, of individual radial velocities of regions on the surface of the sun. And what this will allow you to do, of course, is kind of see what these individual with these modes of oscillation look like. Excuse me. But basically, you're taking the light and you're extracting this information from it. And so to move on from here, and I mean this is a very important technique, right? Because typically, if you want to be able to probe the interiors of an object, of course, you can use seismological data, which would require you to be able to be physically at the object to, be able to pick up on these acoustic modes. But in the case of the sun, we can't physically, of course, go to the sun, so we have to extract this information from the light we're receiving from the sun. So moving on to the next point, the next topic I wanted to discuss. Of course, we've kind of talked now about the solar interior, and so it's natural, of course, to now look at what's happening on the portions of the sun that are visible to us. And so I initially wanted to go somewhere else with this, but I started thinking like, okay, I don't want to leave this particular topic out. So the next thing we're going to talk about, of course, are solar transits. Okay, there's a fly kind of like tormenting me right now. But next thing we're going to talk about are solar transits. And what solar transits are basically the fact that as we look at the sun, every now and then we see objects passing between the sun and us. Depending on your perspective, I've seen images, of course, of people, of course, catching like planes flying in front of the sun. Of course, they have to use certain filters to be able to even catch an image like that on whatever device they're using to observe the sun. But as far as astronomical objects are concerned, there are primarily 3 different objects that pass between Earth and the sun. One of those objects, of course, and which we talked about in our previous stream, was the moon. Right? It passes in front of the sun, and it can produce solar eclipses. The other 2 objects that are able to pass between us and the sun are the 2 inner planets, being Mercury and Venus. I was going to say Mars for a second there, but Mercury and Venus. And so, and what I'm showing here are examples or depictions of it looks to be like 3 different transits that occurred at least within the past decade or so. Probably 2 decades, actually, now that I'm looking at it. So the most recent transit of Mercury, this would have to be the most recent transit of Mercury. It's being depicted on the left-hand side of the screen, where we're kind of seeing in solar coordinates kind of like the north, south, east, and west positions of the solar disk. The ecliptic, which corresponds to the orbital plane of the Earth around the sun. And then we're seeing also with the red line, the actual path that Mercury took. A few key things here is that we're actually able to see within this particular transit is that it happened, of course, over the course of like a few hours. One thing that we aren't able to see is the rate at which it happens. So given the dynamics of Mercury around the sun, we can expect to kind of see these transits on the order of 7 years. We can expect to see them on the order of roughly about 7 years or so. However, every 7 years, that is. However, in the case of transits for Venus, it's a little bit different, though. And honestly, I didn't even know this until very recently. In the case of transits for Venus, we're actually seeing 2 different transits being depicted in the right-hand side of this slide. We have the top transit, which occurred roughly about 6 years ago. And then we have the bottom transit, which occurred 6 plus 8, 14 years ago. Excuse me. But the key thing about these transits is that they typically come in pairs. That is, you'll see a transit at one point in time, and then 8 years later, you'll see another transit of Venus, but on the opposite hemisphere of the sun. But even though they occur in these pairs, they're still extremely rare. Meaning that once you see a pair, you won't see another pair of transits until hundreds of years later, which is kind of a very interesting fact with Venus in particular. And it's more than likely related to the fact that Venus it's probably related to Venus's orbit, orbital plane, as well as the fact that it's much closer to us, um, relative to, like, for example, like Mercury, which um, which is closer to the sun and has a faster orbital period, or a shorter orbital period. Excuse me. Mars, an inner planet. You know the funny thing about it though, I've never not to say that I haven't had the chance to see a transit, but I've never seen a transit before. I mean, I've only been able to actually see transits, images of them taken by others, but I've never myself like been able to look through a filtered telescope and see a transit myself. I think it'd be pretty cool to see though. One of these days, I'm going to do it. Okay, so moving on to actual objects that are that are that are actually on the solar surface, that you can see on the solar disk. We move on to now what we're looking at is an image, and I think, yeah, this is a video. Perfect. We're moving on to see a video actually of these particular dots or features that we can see on the sun, known as sunspots. Sunspots are known to be regions on the solar surface that exhibit high amounts of magnetic activity. And so in this case, we're kind of showing a few sunspots. I think they're at this moment. I don't know if I see any sort of development. Yeah, a little bit of development happening with these sunspots, but they're basically just rotating around the solar disk, or the surface of the sun. Now, one of the key things that we can note about these sunspots is that relative to their surroundings, in this case, the sunspot being a black region on the surface of the solar disk, and its surrounding being what appears to be kind of like an orange yellowish color, the temperature difference. So, as stated earlier, the surface of the sun is roughly like around a temperature of 5,700 Kelvin. However, these sunspots exhibit temperatures that are as as low as, I think it's like roughly like a difference of like 1,500 Kelvin to about like 3,000 Kelvin difference between the temperatures of where these sunspots are at versus the surrounding um, solar surface. And so that's one important key information about these sunspots. But another very important thing about these sunspots is that because they're regions of high magnetic activity, you can also see other features that are nearby them at times. Exactly, sunspots are cooler. A lunar transit? Are you talking about a response to this video I'm showing here, Peter? Um, but oh yeah, there's also one more thing I also want to state about the sunspots. Um, their physical size. Their physical sizes are typically somewhere like within the range of 10. Uh, I know that like the easy way to remember them is like orders of magnitude. I think they're like 10,000 miles to about 100,000 miles in diameter. Someone would have to verify that, but they're pretty big. Um, is the key thing I want to note here. Their sizes can be, comparable to the size of some of the rocky planets within our solar system, or larger. All right. So moving on. So earlier I stated that, of course, within the regions of these sunspots correspond to regions of high magnetic activity, and there's a possibility of being able to see other types of features that arise on the solar surface that are in the vicinity of these sunspots. One particular thing that you can see are flares, solar flares in particular. And so the production of solar flares is related to a concept known as magnetic reconnection. And so to kind of simply explain what magnetic reconnection is, if you could imagine that you have two regions on the solar surface, um, one region exhibiting a particular orientation for magnetic field lines, and another region on the solar surface that's exhibiting its very own independent orientation for magnetic field lines. There are times when you have these regions that are very close, that could be very close to one another, actually interact with one another. And this interaction between their magnetic field lines um, will produce new field or new connections or new field lines that have that exhibit different orientations for the magnetic field lines. But this interaction has the ability to produce large amounts of energy. That is, it can convert this particular process can convert energy stored in the magnetic fields into kinetic energy, specifically like particle acceleration. Particle acceleration. Um, and so, with these solar flares, you typically can have large amounts of particles that are being accelerated. Very explosive moments when these particular events occur. And I am realizing I forgot one very important concept here that's very important with all of this, and that is the solar cycle. So what I was meaning to actually say with the previous slide, now that I think about it, is the fact that these sunspots are linked to what's known as the solar cycle. The solar cycle occurs on time scales of roughly, I think, every 11 years. That's the period of the cycle. And the way in which we can measure this cycle is by looking at the average number of sunspots. Now, what you'd expect is whenever now I don't know if you guys may have heard of this term, solar minimum. So during solar minimum, what you'd expect is for the number of sunspots to be at a minimum or at its lowest. However, as you go through the cycle, the number of sunspots will increase, and eventually you'll reach what's known as solar maximum. Now, with the increase in the number of sunspots, you can also expect an increase in the number of these solar flares. So there's actually a relationship, of course, between the number of solar flares and also the solar cycle. And so this is all important, and I'll get to the reason why it's important in a minute. But there's one more feature that I want to discuss on that occurs on the surface of the sun. That's also tied to this concept of magnetic reconnection. And for the most part, no, let me not say that. I was going to say for the most part, it exhibits energies that are like comparable to the solar flares, but I believe the energies of these events are much higher actually. And these particular events are coronal mass ejections. I'm going to take a moment to quickly look at comments here. And so, yes, flares can be very dangerous. That is correct. Now I was going to come back to that in just a minute. Yes, I've seen the moon pass between the Earth and the Sun very recently, actually, with the total solar eclipse, which was really cool. I hope everyone that's here for the stream was able to actually see it. Um, but yeah, flares can be very dangerous. But even more dangerous are these coronal mass ejections. Um, so in the case of the solar flares, Um, the reason why these particles, especially the charged particles, that is, um, they're accelerated, but for the most part, they stay with the magnetic field lines that are causing the particles to move in the first place. Oh, that's a shame. I'm sorry to hear that, Plank. Um, I hope that someone was able to, of course, take some images or video. I'm pretty sure there's a video out there that kind of showed it. But it was pretty cool. I mean, the next one's going to be coming up soon. I believe that someone stated in the previous stream that it will be back. That is a total solar eclipse. Will be back in 2024. Um, and so you'll get another chance to see it. Um, but and I think it's actually going to be here in the United States. I think someone would have to verify that for me. But getting back to the topic of coronal mass ejections, or you may see them short as CMEs. These are also highly energetic events that occur on the surface of um, of the sun. And the key thing here is that these particular events, I mean, quite literally, eject a lot of, and I mean, they are exactly what the name is supposed to mean. They are large amounts of solar like material, mass from the sun is being thrown out into the universe violently. And so what I'm showing here is actually two two videos. Oh, that's right. I actually also even state where I'm getting this information from. The previous video, I think it was taken from they were both taken from satellites that observe the sun. This particular one was taken from the SDO, the solar. Oh man, Solar Something Observatory. It's taken from the SDO. You'd have to look up what the acronym stands for, because I'm right now forgetting what it means. Solar Dynamics Observatory, and this one is taken from SOHO. So both of these are space-based observatories that are observing the sun, and I think they're observing the sun in the wavelengths of, I think, like visible to ultraviolet light. But for this particular these particular videos that I'm going to show you here, these are two CMEs that are 13 years spaced apart, and they're of course being generated by our sun. Now, the CMEs are being imaged by what's known as a coronagraph. And so we're gonna essentially gonna block out the solar disk, but however leave just enough of the sun visible to the point where we can see the corona, which is where these events are occurring at. And so I'm gonna go ahead and start off by showing the left video, where what we're essentially seeing is a CME, right? It's blowing off a large chunk. In all honesty, it's not an extremely large chunk, but it's a nice chunk of the solar corona. A lot of this mass is being ejected out into space. And then if we move over to our video on the right, in this case, this is a particular CME where I like to say it's almost like looking down the barrel of a shotgun. So in this situation, the coronal mass ejection is directly along the line of sight of this instrument. Now, like I said, it's almost like looking like down the barrel of a shotgun, which kind of brings me to the very last slide for today's discussion, and that is, all of this stuff is very important. These interactions or these events that are occurring on the solar surface affect the regions that are around the sun. I mean, we're the third rocky planet from the sun, and it heavily affects us. And so, this particular field of science, where we're looking at how these highly energetic particle events affect how affect things that are happening either here on Earth's surface or up above our atmosphere, directly above our atmosphere, is known as space weather. And I'm about to talk about. I'm going to end with space weather, but I want to quickly show this video of what we're kind of expecting when a coronal mass ejection kind of goes off in the direction of the Earth. And this is actually a video that I got on Wikipedia. And so I'm going to go ahead and play it. But basically, we have the Earth, in space, doing its thing, rotating, and we have the solar wind, which is basically a stream of particles that are originating from the sun, and they're kind of like linked to the sun's magnetic field. But what we're kind of seeing here, though, is like if you notice, the solar wind kind of went from a relatively quiet stream of particles to like this like really crazy stream of high velocity particles coming from the sun. And now kind of what we're looking at here is our Earth's magnetic field, of course, doing its job in protecting us from high energetic particle events like this. But I mean, as you can almost, just think about it. I mean, the number of particles, you can clearly tell that the number of particles is increasing. It's insane, right? And so during moments like this, during like coronal mass ejections from the sun or solar flare events, you get this increasing number of particles, charged particles, and they can play or they can have an extremely high toll, on electronics either on Earth or electronics orbiting Earth, or people orbiting Earth at that. So, um, yeah, space science is very important in being able to kind of get a sense of, knowing when these events will occur. Well, you really can't know when the events occur because they're kind of random, but at the very least, well, what I mean by that is you can't predict. You can't predict when an event will occur. You can observe the sun and kind of get a sense of, you can observe the sun, knowing the solar cycle, of course, and get a sense of, when or the chances of an event occurring, one, and probably can kind of get like a sense of when you need to be most vigilant as far as these events occurring on the solar surface. But yeah, these are very high energetic particle events, and they affect our electronics. And understanding these events is highly important to, of course, be able to protect our electronics and people, astronauts, that are in space when events like this occur. Okay, well, that was pretty much my discussion here on the sun. I mean, the sun is it's a pretty there's a lot more that can be talked about here. A few minutes warning, right? Because of course, light coming from the sun will reach us before the particles reach us. Yeah, right. Our magnetic field acts like a space sweater. Okay, so I need to take a moment to catch up with comments and or questions. Oh wait, it's going through Carbondale again? Because that's where I was at. In fact, yeah, I think I met some of you guys there. But yeah, it was we were all in Carbondale and couldn't see a thing due to the clouds. Well, I was able to see a little bit of it, but not the entire thing. There was a kid that was actually watching the solar eclipse, and like she started like crying. She was bawling, and I mean, it didn't bring a tear to my eye, but it was definitely an amazing event. And I even made a few jokes as to how it kind of reminded me of like the Death Star. It was probably the Death Star powering up, getting ready to like blast us out of the universe or something. Um, so the ISS, from my understanding, does have a region aboard, in which the astronauts can jump into and protect themselves from these high energy events. Wait, the observing site at Carbondale saw everything. Oh, where were you at? Well, there was I do remember there was a few people who actually like jumped into a truck and they booked it to be, and they were able to see a lot more. It depended on your perspective or where you were at in Carbondale. Where I was at, I was inside of a stadium, and the clouds kind of blocked out a significant portion in time of um of the eclipse. But yeah, guys, our sun's amazing, right? I mean, besides of course space weather, being able to look at how that particular interaction between our sun and the Earth. There is the fact, of course, that the light coming from the sun, of course, as earlier stated, um, provides, as Peter stated, it provides, warmth for us, right? It provides heat. And we need that, of course. All life on Earth needs heat. And also, it provides a source of energy for plants, of course, that are kind of at the bottom of the food chain to produce their own food and be able to pass that energy along to us, us animals that can are either herbivores or carnivores and stuff like that. Herbivores as well. So herbivores, carnivores, and omnivores. Oh yeah. Oh yeah, Noel. Rovers need heat too. Yeah. Um, what was that? So I mean, honestly, I don't keep up with the rover missions as much. But I did, of course, take the time to listen to Wednesday's stream of Pamela covering the possible Oppie. I don't know how Oppie is actually. Does anyone know have an update on Oppie? Because it was funny though. I was listening to the stream, the NASA stream, and they were talking as though Oppie, is a human being, right? A lot of personification was going on in the conversation, and so, but I can completely understand it. Of course, this is their baby, and their baby's on another world, and just trying to survive, right? Exactly. It had to hunker down, and so is the storm still occurring? I don't know how long the storm should last. Yeah, for those of you who do not know, there is a rover on Mars. It's been nicknamed Oppie, and I believe its primary mission is to observe or to gather and analyze Martian rocks. I might not be telling the entire story there, or I might be complete. Well, no, I think it is to gather and to observe Martian rocks. But it was initially meant to only be on the surface and observe or do its analysis over the course, I believe, of like 90 days. But as Noel has stated, it's been there now for 14 years, right? It's a teenager right now. It's a teenager. We got a robot teen living on Mars right now, and so the key thing here though is that as let's see, someone just mentioned it. Right, Noel just mentioned that rovers need heat too. I think what's happening with the sandstorm is that it might be blocking off, Oppie's ability to get, I guess, solar radiation to keep it hot. Um, yeah, supposed to last 90 days. Oppie is a survivor. No human can do what Oppie's done. Of course, Oppie doesn't need oxygen, or it doesn't need an atmosphere like we do. It doesn't need food. It doesn't need water. So yeah, it doesn't need. Apparently, it doesn't really even need. Well, it needs shelter, but I mean, it's making it. It's surviving. But yeah, a planet-wide storm. Yep, it needs that warm light from our sun. So it needs the warm light. It needs the light from the sun for solar power. Okay, not so much for heat. Or I guess that because when I caught the stream, I kind of caught it a little bit late because I had to go do something else. But wait a second, it doesn't. So yeah, I think I missed some of the. So as I stated earlier, guys, I don't know much about the rover missions, but it's not being powered by nuclear energy. I did think I remember catching that part. The particles from the storm will allow for the solar panels to be clean, which is actually pretty cool. Actually, the thing that could possibly kill it will also make it cleaner. All right, guys. It's got a small battery to keep the clock and other primary systems going for. Ah, I see. Well, thanks, Adam. Yeah, guys, I love our conversations. Um, it is definitely like a point of my work day that I look forward to on Wednesdays and Fridays. I was actually kind of sad because me and Joe were on standby during the press or the stream, the NASA stream on Wednesday, and so we were like in the background. We were waiting. We were like, okay, they're going to end it in like 30 minutes tops, and then we're going to be in, and we're gonna do our thing, right? And yeah, 30 minutes went to like 45 minutes, and 45 minutes eventually, ended up in a total time of an hour. And so kind of not midway through, but like around a 45-minute mark, we decided to just call the stream. We was like, okay, we'll just move the stream, to Friday and present it then. But guys, again, thank you for tuning in today. This has been another stream of CosmoQuest Astro 101. We will be back again next Wednesday after Daily Space, which will air at 12 o'clock p.m. Central Time. I'm going to try my best to start getting better at presenting the time in different time zones. My best right now would be that 12 o'clock p.m. Central Time corresponds to 1 o'clock p.m. Eastern. All right, guys. I will see you guys later. You guys have a good weekend. All right. Oh, and for all you fathers out there, happy Father's Day in advance. All right. Bye.